So today we're going to be talking about the concentration of solutions. So we talked yesterday about if something was saturated, supersaturated, if it was concentrated or dilute. So today we're actually going to do the calculations that determine the actual concentration. So this first blank is molarity, which is going to be the most common of the ones we're going to use. And anytime you have been doing lab and you had a liquid and it said use like 100 milliliters of like 0.5 big M solution, you never knew what that big M is. That big M is actually the molarity, which tells us the concentration. So we designate big M molarity. And the formula is moles of solute over liters of solution. Oftentimes we will just abbreviate as mole over a liter. Okay, but you need to understand that it's the moles of solute on the top and it's the liters of solution on the bottom. Okay, and it does have to be in liters. So most of the time you're going to be given the problem in milliliters because that's what we go in the lab and measure in. And so you'll have to convert that really quickly in your head by dividing your milliliters by 1,000. So we'll do a couple of sample problems. First one is calculate the molarity of a solution prepared by dissolving 11.85 grams of potassium permanganate in enough water to make 750 milliliters of solution. So first thing we need to know is how do I write the formula of potassium permanganate? Does anybody remember? KMnO4. So we have KMnO4. Okay? So if we have 11.85 grams of KMnO4, I need to get 2 moles because remember molarity is moles over liter. So how do I get from grams to moles? Molar mass. Okay? I will give you that the molar mass is 158.04 grams in 1 mole. And when I do that math, I should get 0.075 moles. So now in order to get to molarity, I'm going to divide by the liters of solution. And so it gave us 750 milliliters. If I divide that by 1,000, it's 0.750 liters. So I'm going to divide by 0.750 liters. And then you just divide, and you should get 0.100 molar when I have the correct significant figures. Okay? Pretty straightforward. Okay, I want to do the couple of examples because sometimes you don't always get it like that. So these are going to go on page 154 of your interactive notebook, and we should have our phones put away during this time. Okay, so we're going to do this problem. Oh, I got to erase that. So in this case, we're going to have, we have 225 milliliters of 0.175 molar sodium hydroxide. And my question is how many grams of sodium hydroxide would we need to make it? Okay, so this, you can just write this on the back and transfer it to page 154 later if you want. So I need to know how many grams, so I've got to get to moles. So the way I can get to moles when I have a molarity, remember that it's 0.175 moles per liter, and it's moles of NaOH per liter. So what can I do to get rid of liters? I only have one other thing in the problem. What can I do to get rid of liters? If I have liters on the bottom, how do I need to get rid of it? Put it on the top. Okay? So I'm going to take this 225 milliliters and multiply it by 0.225 liters. Okay? Then that will give me 0.394 moles of sodium hydroxide. And then how do I go from moles to grams? The molar mass. So I take moles of sodium hydroxide. And you can do it all in one step. I just was running out of room. Times the molar mass of sodium hydroxide is 40. So I would need 15.8 grams of sodium hydroxide. So to make that solution, I would mass out 15.8 grams of sodium hydroxide, and I would add it to 225 milliliters of solution of water, and I would get the 0.175 molar. So that's one example. Another example, I'm sorry if I just erased that too quickly. I probably did, I'm sorry. Another example is if I wanted to know what volume would be added to make .250 molar if all I have is 48.5 grams of salt. So I have 48.5 grams of salt. I want to make a 0.25 molar solution. How much water would I need to add? Okay, so first thing I need to do is convert grams to moles. Molar mass is 58.44. So I got rid of grams. Now I can get rid of moles by using the molarity, because molarity is moles per liter. So I would say 0.25 moles on the bottom per 1 liter on the top. And then my moles would cancel out, and I would get that I needed to add that to 3.32 liters. So if I added the 48.5 grams of grams of salt to that much volume of water, I would have a 0.25 molar solution. Okay, so that's molarity. That's your molarity practice. So then we're going to talk about concentration of ions, which is a concept that's going to be very important for us to do as we go forward from this point on. So whenever I have a solution, and if I tell you it's 0.25 molars of sodium chloride, I actually have also 0.25 moles of sodium ions, and I would have 0.25 moles of chlorine ions, okay? But what happens is when they break apart and it's not even, this is where kids get a little bit confused. So when the calcium chloride breaks apart, it gives me 1 calcium and 2 chlorine ions. When sodium phosphate breaks apart, it's giving me 3 sodium ions and 1 phosphate ion. And that affects the concentration of the individual ions. So if I had calcium phosphide, let's review how we write formulas. How do I write the formula for calcium phosphide? P2. When that breaks apart, because it's ionic, I'm going to get 3 calcium ions, and I'm going to get 2 phosphide. So if I start out, I'm going to change colors so I'll see this. If I start out with 0.25 molar of calcium phosphide, when it breaks apart, I actually get 0.75 molarity of calcium, and I get 0.5. And the way I got that is I just took the coefficient and I multiplied by it. So when that particular thing breaks apart, I actually get 0.75 molarity of calcium, and I get 0.5. So all I did was take the coefficient here and multiply. For silver sulfite, you have Ag2SO3. When it breaks apart, you get 2 silver plus 1 sulfite. So if I start out at 0.33 of the total, that means I would have 0.66, and then for the sulfite I would just have 0.33. That's going to be an important concept, that you understand that it does that, and you don't forget it. And I can tell you in AP Chem, that's something that trips kids up all the time. They forget to do that part. They forget to say, oh, there's 3 when it broke apart, and they forgot to triple their concentration. So that's an important thing to get down now. I'm sorry, what? Mm-hmm. Does anybody have a question on that? Got it? Okay. Next one we're going to talk about is something that's similar to molarity. It's called molality, just to keep it nice and confusing. Change one little letter. Molality, and it is signified with a little m, and that's moles of solute, which is the same as it was for molarity, but on the bottom it is kilograms of solvent. So the bottom is not the whole thing, it's just the solvent, and it's in kilograms. And when we, later on, that looks like an R, I'm sorry. Make sure y'all know that's an L. Molality, okay? When we do colligative properties, which is the last thing we'll do for this unit, they have to be done in molality, okay? All the other times we're going to be using molarity. When we make up solutions for labs, it's always in molarity, but when we do the colligative properties, we have to use molality. And of course, we signify that as moles per kilogram. Okay. Same concept for the calculations. So I'm only going to do one of those because it's going to be very similar, except instead of using liters of solution, we're going to be using kilograms of solvent. Okay. So our sample problem here is calculate the molality of a solution prepared by dissolving 15.54 grams of potassium hydroxide into 750 grams of water. So again, we have to get to moles. So we have 15.54 grams of potassium hydroxide divided by the molar mass of potassium hydroxide, which is 56.11. So that gives us 0.2770 moles. And then I'm going to divide that by the kilograms of solvent. If I have 750 grams of water, there's 1,000 grams in a kilogram, so divide by 1,000, so you get 0.75 kilograms. And then your molality is 0.369, little m. So pretty much the same concept, it's just something different on the bottom. Everybody have that before I move on? That's for left side, you already have that. All right, concentration of solutions. We're going to talk about dilutions. And dilutions are something that we do a lot of in the lab, is when we have something concentrated. Like we buy all of our acid in a concentrated solution because it's cheaper and it's easier to store, and then we dilute it, okay? And so you have this M1V1 is equal to M2V2, where M1 is the initial molarity, or the concentrated molarity. So initial, which will always be more concentrated, and then final molarity. Initial volume and final volume are the other two. I want you to clean up the lab and then set that lab stuff out. Okay, thank you. So initial volume, final volume. And this example is how would you prepare 485 milliliters of 0.39 molarity solution of NaCl when all you have is a 1 molar solution. When you have 2 molarities listed, your higher concentration will always be M1. Okay? M1 will always be your higher concentration. So So we know that this one is going to be M1, so that's got to be M2, and then of course the 485 goes with it because it says you have that much of it. So that's V2. So we're actually going to be solving for V1, okay? So, which is actually something I would do quite a bit. I would say I need to have, you know, a liter of 0.5 molar solution, and I've got to start with 16. So how much of the beginning stuff do I need? So most oftentimes we're actually solving for V1. So when I rearrange that equation, it's going to be V1 equal to M2 V2 over M1. Okay? And in this case, it's okay to go ahead and leave it in milliliters. You don't have to cross it out because you're going to cross out your molarities. So even though molarity is moles per liter, the fact that you're going to cross out both units, you can leave your volume in milliliters. Because most likely you're going to go and measure milliliters anyway. We very rarely measure a liter of something in there. So I just plug it in. I have 485 milliliters times 0.39 molar divided by 1 molar. And so my molarity cancels out, and I get, I think, what did I get?
Do you know what's up with the broken test tube?
Yeah, it broke. I have to just throw it away. It cracked.
I didn't know if it was...
It was hot when it cracked, so I forgot to clean it up.
Okay.
So you get 189 milliliters. So what I would do if I was going to make that, I would take 189 milliliters of the 1 molar solution, put it in a container, and I would add enough water to make 485. Okay, I wouldn't add 485, so make sure you understand that. So I would actually end up adding like 296 or something like that. So I would take the 189, add 296, so that I could get a total of the 485. So make sure you understand that when you're working your dilution problems. Don't just put that you have to add that much 485. No, you're making it up to that volume. So you have to subtract out the original volume. The second to last type we're going to talk about is percent mass, which is basically just a percentage problem. It's the mass of the solute over the mass of the solution. And just make sure you know when you're talking about mass of solution that within that solution you have the solute plus the solvent. So you have to add those together. So make sure you know the mass of the solution is solute plus solvent. And these are going to be pretty straightforward algebra problems. So this one wants to know how many grams of sodium chloride would be required to make a 10% solution if you have 50 grams of water. So you're going to be solving for how much mass of the salt do you need. So you're going to plug that in, and you're going to have x over x plus 50 equals 0.1, because I went ahead and take it out of the percentage. If you don't understand why I did that, stop me now. And then it's just solving for x. So go through and cross multiply, and you get x is going to be equal to 0.1x plus 5. Do I need to go through this, or can y'all figure this out from here? Subtract 0.1 from both sides. Then you have 0.9x equals 5. So then x is equal to 5.56 grams of sodium chloride. So I would get 5.56 grams of sodium chloride and add it to 50 grams of water, and I would have a 10% solution by mass. Okay? And then the last one is percent by volume. Does everybody have that before I move on? And same thing, it's instead of mass of solute, it's just volume. And again, when you're talking about volume of solution, remember that that's solute plus solvent. So same concept here. Matter of fact, I'm going to let you work it out and see if you get the right answer. I'm going to tell you that it's 100 milliliters should be your answer. So I'd like you to try it and tell me if you get it. But I'm going to stop the video here.